We on? Okay. All right. This is the first in a series of videos that we're going to be showing this semester. They'll be on YouTube, and we'll give you all the details in the lecture. We're going to start this off with sort of like a brief description of some of the reactions and the mechanisms that aldehydes and ketones undergo. All right. And so this, just to refresh your memory, this is what the carbonyl group looks like. And the major thing about this, the thing that really affects the chemistry of these, is the fact that this carbonyl group is extremely polar. Right? You can see from this, from these two resonance forms, how the charge gets separated. Right? The oxygen, because of its high electronegativity, tends to pull electrons out of the pi bond, and it imparts a negative charge onto the oxygen. At the same time, we have electrons being taken away from the carbon, so the carbon takes on a significant amount of positive charge, with the result that it becomes quite electrophilic. All right? And that's sort of like the basis of the reactions, most of the reactions that we're going to see with aldehydes and ketones. You're going to have a nucleophile coming in, hitting this highly electrophilic carbon, and we get this intermediate here. Okay? Now this is a very important structure as far as carbonyl chemistry goes. This is what's referred to as the tetrahedral. All right.
Sorry.
Should we stop it or?
No, let's continue.
All right. Okay. John, Mary?
Hi.
How are you? Okay.
We're good.
Don't cut that out, okay?
We love you.
I know, I love you too. I love you right back. All right, so as I said, this carbonyl carbon is going to be quite electrophilic because electrons are being sucked up from it by the oxygen. Okay? Now, when the nucleophile hits the carbonyl carbon, we get a complete shifting of the electronic structure of the carbon. Okay, it goes from sp2 to sp3, and that's the reason why we call this a tetrahedral intermediate. Right? It's because what happens is that we go from this trigonal planar structure to this tetrahedral structure. All right, and this is an intermediate that we're going to see in just about every reaction involving a carbonyl. Okay. Okay. A good example of one of these reactions. All right, a good example of this type of reaction involves Grignards. Now, just to refresh your memory, we talked about Grignards towards the end of last semester, and Grignards are actually quite easy to make. All you have to do is take either a primary or a secondary alkyl halide, react it directly with magnesium. The only precaution that you have to follow is you have to make sure that you use a polar aprotic solvent, and the one of choice is usually some sort of an ether. Okay, in this case, we've used diethyl ether, but we could also use THF, tetrahydrofuran as well, or any ether will work. The reason why we need an ether is because ethers are particularly effective at dissolving these organometallic compounds. Okay. All right. So the way the reaction goes is we have this highly nucleophilic carbon from the Grignard, comes over, hits the carbonyl. We get the tetrahedral intermediate. Now, there's one other thing that you should notice here, and that is that this magnesium fragment remains sort of tied to this negatively charged oxygen. It's kind of like an ion pair. And this is important because what it does is it stabilizes this negative charge for a short period of time. Okay? Now, in the second step, what we have to do is we have to get rid of this negative charge on the oxygen, and probably the best way to do that is just by protonating it. So all we have to do in this second step, and this is a distinct second step. We can't do these all together, right? We use either dilute acid, or we could even use water. A proton gets ripped off from the, in this case, the hydronium ion. We end up with an OH, and it's a stable compound. It's a tertiary alcohol. Okay. The magnesium is precipitated as magnesium hydroxide, and this is really an important reaction because what it does is it enables us to make bigger and better molecules. Okay, it's one of the more effective ways of making carbon-carbon bonds. Okay, all right. Now, another example of this, we can use another well-known nucleophile, one that we saw a lot of last semester, and that is cyanide. Okay, and what we're doing here is we're adding cyanide in the form of sodium cyanide, And it follows just about the same reaction pathway. The cyanide ion comes in as a nucleophile, hits the carbonyl carbon, drives a pair of electrons up to the oxygen. We get the tetrahedral intermediate, and then in the second step we protonate it so that we end up with the final neutral compound. And these compounds are called cyanohydrins. I think we talked about those briefly last semester. And they're fairly useful synthetic intermediate compounds because we can do all sorts of transformations of the cyanide. We can turn it into an amine, we can hydrolyze it to an acid, and other things as well. Okay? All right, now, before we go any further, we should take a look at what affects the reactivity of these carbonyls. All right, there are a couple of things. Okay, first of all, obviously it's steric. Generally speaking, the aldehydes are going to be more reactive than the ketones, and as you can see from this diagram that we have here, and the reason is pretty obvious because with the aldehyde we've only got one alkyl group flanking the carbonyl, whereas with the ketone we've got two. So in other words, this site here, this carbonyl carbon is a lot more congested than it would be with the aldehyde. Okay, so that's the first thing. That's probably the most obvious thing. Now the other thing is a little bit more subtle, all right, because if you recall, when we go back to the mechanism, you remember after the first step, or in the first step, we transform this sp2 carbon to an sp3, which means that the bond angles change. So instead of having these two alkyl groups at 120 degrees, what happens is that they go to 109 degrees, or approximately that, and they become closer together. All right, this also introduces steric strain. Okay, so that's the first thing that affects the reactivity. It's steric. Okay. Okay. Now, another thing is this is the just to go back to the steric thing. This is the angle at which the nucleophile comes in. All right, it comes in at a kind of a sharp, steep angle, almost perpendicular to the plane of the carbonyl group. Okay, and we'll get into this. Okay, it turns out that there's a very good reason for this, very precise angle at which the nucleophile hits. It has to do with the molecular orbitals, but we'll do that at a different time. Okay. Now, as we said before, the ketones are generally less reactive than the carbonyl, than the aldehydes. And the reason for that is electronic, because if we take a look at this, okay, remember we said that the thing that makes this carbonyl carbon electrophilic is the fact that electrons are being pulled away from the oxygen. But the thing is, if we take a look at what else is attached to the carbonyl carbon, we've got these alkyl groups, okay? And as you recall from our discussions about carbocations, you remember that these alkyl groups will donate electron density through through hyperconjugation, okay? Hyperconjugation. All right. So I mean, obviously, if you've got a ketone, you've got two alkyl groups pumping electrons into this site. And really, if you pump electrons into the site, it becomes less electrophilic. And if it's less electrophilic, it means it's going to be less reactive. Okay, and that's not the case with the aldehyde. With the aldehyde, we've only got one alkyl group, so therefore there isn't going to be as much electron density transferred into the carbonyl carbon through this hyperconjugation. Okay. So because ketones in general are more highly substituted, the incoming path of the nucleophile is obstructed, and due to the additional alkyl groups adding more electron density to the carbonyl carbon, it's going to be less electrophilic and less attractive to nucleophiles. Okay, now there's another thing that we should take into consideration too, and that is that if we stick any kind of electron withdrawing group on one of these alpha carbons, whether it's an aldehyde, whether it's a ketone or an aldehyde, that will also increase the electrophilicity, okay? Because that will also pull electron density away from it and make it more electrophilic. Okay? Now, the next topic, these reactions that we just talked about, the Grignard and this cyanohydrate reaction, these all involve the use of really strong nucleophiles, but we can also get weak nucleophiles to react. Like, for example, water will react with a carbonyl to a very, very small extent, and it forms a compound like this. This is either called a gem diol or a hydrate. Okay, so this is a hydrate. Okay, so the electronic and steric effects can be very, very well illustrated if we compare the equilibria of various, the formation of various hydrates. Okay, so what we're going to be looking at in the next slide is this ratio of hydrate to the carbonyl. Okay, when this reaction reaches equilibrium. So let's take a look at that. Okay, so here are a couple of examples. Now, this actually could be considered to be an equilibrium constant. So you notice that if we take formaldehyde and we put it into water, it's going to be just about completely converted into a hydrate. I mean, just take a look at that value there. It's 3 orders of magnitude. Now look at what happens when we just add a single methyl group. Look at what it drops down to. Okay, it's only 1.06. So this shows the effect of these alkyl group substitutions. Okay, and as I said, it's a combination of things. First of all, it's electronic, where this is pumping electrons through hyperconjugation, and also it's steric. Okay. Now, if we go to acetone, look at what happens here. It drops way down. Okay, it's about 1,000th of what this is. Once again, it's a combined effect of these two methyl groups. Now, look at what happens here. Here, what we've done is we've replaced 3 of the hydrogens in the acetal with fluorines, and we all know that fluorines are quite electron withdrawing. And you notice that the equilibrium constant jumps way up again. Well, not way up, but I mean, it changes significantly over the acetone. If we take this compound here, where we replace one of the hydrogens with just a single chlorine, because we've only got one chlorine, and because chlorine is a lot less electronegative than fluorine, we only get a value of 0.11. Now take a look at this guy here. Now this is really kind of an unusual, well, not unusual, it's kind of a neat example, because you notice that this would be benzophenone, okay, benzophenone, right? And here we have the carbonyl directly attached to the benzene ring. So what do you suppose happens to the positive charge which develops on the carbonyl carbon? Toby, what happens?
It should be less susceptible to attack.
What?
It should be less susceptible to attack because of how sterically hindered it is.
Well, that's true. Yeah, right. There's steric hindrance, but there's another thing going on too. What's going to happen to the? Yeah, John.
Resonance.
Oh,
Right. Okay. Resonance. Really. What did John say? Resonance.
They're going to be like conjugated electrons, so it's going to be like an electric charge, so it's not going to be susceptible to attack.
Well, yeah. Okay. So another way of putting that is that the positive charge that would develop here to make it reactive is going to be delocalized around the whole brain. Okay. Okay.
I failed.
What?
I failed.
Okay, so now with this reaction here, these reactions with weak nucleophiles can be sort of enhanced by making the carbonyl carbon more electrophilic. Okay, so what I'm saying is that if you take this compound here, as we saw from the previous slide, this is going to be a lot. This is not going to be very reactive. Particularly to a weak nucleophile like water. But what we can do is we can sort of beef up the electrophilicity of this carbon by making the oxygen more electron withdrawing. And it's very easy to do. All we have to do is just add an acid. Because if we add an acid, this oxygen is going to be protonated, takes on a positive charge, and as a result, it's going to become even more electron withdrawing. So this would be the first step in this, okay? And one of the things that you have to keep in mind is that whenever we're dealing with these reactions, these nucleophilic addition reactions involving a weak nucleophile, they're always going to be reversible. Okay, well, the Grignard for all practical purposes goes to completion because it's such a strong nucleophile. Same thing is largely true with the cyanide. But with something like this, where we're using water as a nucleophile, it's always going to reach some sort of an equilibrium value. Okay? So the mechanism here is pretty much the same as the mechanism that we saw earlier. It's got some added steps to it. First of all, we have to protonate it, as we did in this step here. Next, the water molecule comes in, the oxygen is the nucleophile, comes in, hooks up to the carbon. We get the tetrahedral intermediate. But now, in order to generate a stable compound, we have to deprotonate this. So another water molecule will come in, pull this off, and we get our hydrate. Okay, we get our hydrate. And you notice that the acid is acting as a catalyst because it gets regenerated. Okay, now we said that these hydrates are generally pretty fragile compounds. They break down very easily. This is an exception. All right, this is a compound called chloral. All right, it's ethanol, which has where 3 of the hydrogens have been replaced by chlorine, and it turns out that this will be just about 100% converted into the hydrate. Why would that be, Toby?
Why always me? Those go ahead. Can I ask someone else?
Yeah, all right, okay, so anyway, what happens is, just like we saw before, remember when we had those examples in that previous slide, the one about 2 or 3 back, whenever we stuck electron withdrawing groups onto this alpha carbon, it made the carbonyl much more electrophilic. Okay, so that's what's going to happen here. Okay, that's what's
Yes.
Yes. Okay. Good. All right. Okay. Okay. So now this is a really important reaction. We're going to be seeing a lot of this. I only started it off on this page here, but alcohols are also weak nucleophiles. So once again, because they're weak nucleophiles, we have to start off the same way as we did with the hydrate. We have to protonate the oxygen first. That makes the carbon sufficiently electrophilic so that the alcohol can successfully attack. All right, so that's what we see happening in this step here. All right, so we've got the protonated oxygen. It increases the electrophilicity of the carbonyl carbon, right? Sufficiently for this alcohol to come in and successfully attack this. Okay, so we get this tetrahedral intermediate. Obviously, the next thing we have to do is to get rid of this hydrogen here, so that we have a neutral compound. Okay, so this compound is referred to as a hemiacetal. And what we've done here is we've added one equivalent of the alcohol. Now, usually the reactions, if we're dealing with an open chain, either aldehyde or ketone, it doesn't stop here. We'll keep going. The only time we're going to see stable hemiacetals is if you have a cyclic compound like this. All right? These are going to become quite important later on in the course when we talk about carbohydrates, because most of the monosaccharides, you know, glucose, arabinose, all of those, they exist as a cyclic hemiacetal. All right, we'll see that later on. Okay, now, as I said, this reaction usually doesn't stop at this point. It keeps on going. Okay, so we have another acid comes in, another hydronium ion, further protonates the oxygen, so that now we have a very good leaving group. Okay, we've got a water molecule here. Okay, and that's what happens in the next step. What happens is that this water molecule gets kicked out, and what kicks it out is the lone pair on this alkoxy group here, this methoxy, right? Pair of electrons, you know, one of the lone pairs off the oxygen sort of loops up, forms a double bond, boots that water molecule out, so that we now have this intermediate here. Okay. All right. Now, this actually is fairly stable because it's because of resonance. All right. And these are the 2 resonance forms of this intermediate. So this intermediate is actually pretty stable. Okay. Now, what we've generated here is another very electrophilic carbocation. Well, yeah, it actually is a carbocation. And what's going to happen is that we're going to have a second alcohol come in, hits this, we get this tetrahedral intermediate, this gets deprotonated, and now we have this compound here, which is called an acetal. Okay? And these are actually quite important. Okay, we'll give examples of their importance in the lecture and in a later video. Okay, these actually act as very, very effective protecting groups for carbonyls.
What's a protecting group?
Well, Billy. No, a protecting group, well, I don't think I have an example here. But let's say that we had this carbonyl on the same molecule that we had, say, a double bond, an alkene. And let's say that we wanted to reduce the alkene, but not the carbonyl. So what we would do is we would first turn the carbonyl into this acetal. Then we do a catalytic hydrogenation to reduce the double bond to a single bond, and then we get rid of this. Okay? So that's another important feature of any kind of a protecting group, because they're easy to get rid of. Right? It's easy to reconstitute or go back to the original carbonyl. All you have to do is just take this, cook it up in some dilute acid, and this will spontaneously go back to the carbonyl. Essentially, what we'd be doing is driving this reaction backwards. And since it's reversible, all the steps are reversible, it's fairly easy to do. Okay? Okay, that's all we're going to do for now. I'm sorry about the ragged performance. All right, this is my debut, so I promise that the production qualities will increase. All right, thanks for your attention. Adios.